early 1926, Erwin Schrödinger published a series of papers that completely reshaped physics. Over the previous 3 decades, it had become increasingly clear that existing physics approaches simply didn't work at very small scales. The equation at the core of Schrödinger's papers effectively replaced Newton's second law at the atomic scale, describing the behavior of particles like electrons incredibly accurately. Schrödinger's equation is very similar to the heat and wave equations from classical physics, with one exception: the imaginary number I. What is the I doing here? Schrödinger's equation critically and controversially replaces the notion of a particle with a wave, and says that for a given point in space, the value of this matter wave changes in time proportionally to the curvature of the wave in space. This proportionality makes a ton of sense for the heat equation. It tells us that, for example, in regions that quickly change from cold to cold, the hot area will become cooler as the heat spreads out. But in Schrödinger's equation, the time derivative is multiplied by the imaginary number I. How does multiplying by I turn a heat equation into an incredibly accurate description of matter itself? Imaginary numbers would go on to play a central role in quantum physics. What makes imaginary numbers so useful in one of our most fundamental and successful theories of nature? In 1925, Einstein published this paper, where he referenced a recent PhD thesis from an obscure Frenchman named Louis de Broglie. 20 years before, in 1905, Einstein and Max Planck famously showed that light comes in discrete packets that we now call photons, and that the energy of each photon is related to its frequency by Planck's constant. In his thesis, de Broglie showed that if he treated matter not as discrete particles, but instead as waves, and extended the Planck-Einstein relation to these matter waves, he could accurately predict the behavior of the hydrogen atom. When Einstein's paper reached the physicist Erwin Schrödinger, he quickly realized that de Broglie's work was a more elegant and general version of his own investigations into gauge theory, and became obsessed with the idea that matter might actually be a wave. After giving a talk on de Broglie's matter waves at his home University of Zurich in November, Schrödinger's colleague Peter Debye remarked that this way of thinking was childish, and that if matter waves were real, there would have to be a matter-wave equation. This comment stuck with Schrödinger, and when he left for winter holiday in the Swiss Alps a few weeks later, he brought along his papers and books to work on the problem. In his room in the mountains, Schrödinger sat down and tried to find the wave equation for matter. Schrödinger began with the classical wave equation, and worked to modify it to be compatible with de Broglie's matter-wave results. In this one-dimensional classical wave equation, y is a function of position and time that represents the displacement of the wave. For example, the position of a point on a vibrating string above or below its resting position, and v is the speed of the wave. A common approach to solving the classical wave equation is to break apart its spatial and time components, resulting in 2 new differential equations, one that depends only on position and one that depends only on time. The position equation roughly says that the curvature of the wave should be proportional to the negative displacement of the wave. This makes a lot of sense in our vibrating string example. A point with high positive displacement corresponds to a high negative curvature, and vice versa. Mathematically, the position equation says that f should be some function of x, that when differentiated twice is equal to itself times some negative constant. Both sine and cosine have this property. The second derivative of sine of k times x is equal to minus k squared times the original function sine of kx, exactly satisfying our differential equation. Importantly for Schrödinger, when we fix the ends of our string, setting f equal to 0 at x equals 0 and x equals L, the length of our string, only very specific values for the constant k will work. Visually, this just means that we can fit half of a sine wave between the fixed ends of our string, or a whole sine wave, or a sine wave and a half, and so on, but nothing in between. This behavior is what gives vibrating strings a very pure tone musically. The frequencies of vibration are simple multiples of the fundamental frequency. This behavior was critical for Schrödinger's attack plan. Like the vibrating string, the hydrogen atom produces energy, but only at very specific frequencies. However, for the hydrogen atom, these frequencies are not at simple even spacings. Schrödinger's hope was that if he modified the classical wave equation using de Broglie's matter-wave approach, the solutions to his new wave equation would match the observed emission spectrum for hydrogen. First switching to the Greek letter psi to represent the matter wave, and rewriting the wave number k in terms of wavelength, Schrödinger then substituted in de Broglie's formula that relates the wavelength of a matter wave to its momentum, expressed as mass times velocity. The constant term in the classical wave equation now depends on the mass of the matter wave squared times the velocity of the matter wave squared. From classical physics, kinetic energy is equal to 1/2 mass times velocity squared. So we can rewrite our numerator as 8 pi squared m times the kinetic energy of the wave. Finally, taking the total energy E as the kinetic energy plus the potential energy V, Schrödinger solved for the kinetic energy and substituted. The hydrogen atom has 1 proton and 1 electron. Schrödinger assumed that the proton was fixed, creating an electric potential for the electron of the charge of the electron E squared divided by the distance r between the electron and proton. Atoms are of course three-dimensional, so we need to expand our spatial derivative to include x, y, and z. From here, Schrödinger needed to find the solution to his matter wave equation, just as we found earlier that sine of kx was a solution for the vibrating string. The math is of course trickier here. Referencing his mathematics books and with some helpful correspondence from the mathematician Hermann Weyl, Schrödinger was able to solve his wave equation for hydrogen. Like our solution to the vibrating string problem, where k could only take on very specific values, Schrödinger showed that the energy term E in his equation was also quantized, and that the spacing of these energy values approximately matched the observed emission spectrum for hydrogen. Schrödinger submitted his results for publication in this paper on January 27, 1926. The response from the scientific community was quick and positive. Robert Oppenheimer later called Schrödinger's result perhaps the most perfect, most accurate, and most lovely theories that man has discovered. And the physicist Paul Dirac remarked that Schrödinger's result contains much of physics, and in principle, all of chemistry. The orbital electron patterns that you may have learned in chemistry class are the solutions to Schrödinger's equation. Now, up until this point, none of Schrödinger's mathematics required the use of imaginary numbers. This would change in the summer of 1926, when Schrödinger expanded his approach to include systems that change over time. Getting the details right on complex topics like this requires a ton of research. Here's all the books I reviewed when writing the script for this video. In Schrödinger's initial approach, he started with the part of the classical wave equation that only depends on position. To completely solve our vibrating string example, we have to multiply our spatial solutions f by our solutions in time g to compute the final position y of each point on the string as a function of position and time. In the classical wave equation, the spatial and time components are the same differential equation, just with different constants. So the solutions in time are also just sine and cosine waves. A helpful mathematical trick used by physicists including Schrödinger is to express these solutions using complex exponentials. So instead of writing the cosine of omega times t as a solution, we instead write e to the power of I times omega t. By Euler's formula, the real part of e to the power of I times omega t is exactly equal to our original cosine solution. Differentiating complex exponentials is simple. We just drop down the exponent. So the first time derivative of e to the I omega t is just I omega times our original function. And our second derivative is just I squared times omega squared times our original function. This shows that e to the I omega t is a valid solution to our differential equation. Importantly, up until this point in physics, although complex numbers were used frequently like this in computation, the final answer was always just the real part of the result, and everything physical in the problem, like the displacement of the string, corresponded to the real part of complex exponentials. To expand his equation into the time domain, Schrödinger started with a complex exponential representation of the wave function as usual, assuming he would be able to take the real part once he was done calculating. Since the energy of a matter wave is proportional to its frequency by the Planck-Einstein relation, we can rewrite this complex exponential in terms of the total energy E of the wave. Differentiating, we can show that the energy of the wave times the wave function is proportional to I times the derivative of the wave function. Now, returning to Schrödinger's time-independent equation, we can isolate E times the wave function and substitute, obtaining the final modern version of the Schrödinger equation. Schrödinger found this path early on, but hesitated to publish it, writing to the physicist Hendrik Lorentz, "What is unpleasant here, and indeed directly to be objected to, is the use of complex numbers. Psi is surely fundamentally a real function." The I explicitly showing up next to the time derivative in Schrödinger's equation means that purely real wave functions will not work. The wave function itself has to be made from complex numbers. As we'll see, the complex wave function and multiplication of the time derivative by I turned out to be a feature, not a bug. It allows Schrödinger's equation to elegantly describe the behavior of matter. Let's consider how Schrödinger's equation applies to a free particle in one dimension, such as an electron far away from any other particles. In this case, our potential energy V is 0. Let's temporarily combine our constants together into a single constant that we'll call C, and set it equal to 0.1, and assume a very simple starting configuration for the wave function, with a value of 1 surrounded by zeros. We can estimate the second spatial derivative at our central location numerically by adding together the adjacent wave function values and subtracting 2 times the wave function at our central location. So 0 minus 2 plus 0 equals minus 2. We can keep track of each part of Schrödinger's equation over time using a table. At time t equals 0, we set our initial wave function value to 1, and we just estimated our second spatial derivative to be minus 2. From here, all that's left to do is to compute d psi dt, using Schrödinger's equation. Multiplying our estimate for the spatial derivative by 0.1 times I, we compute a complex number with 0 for the real part and minus 0.2 for the imaginary part. Now, Schrödinger's equation says that this value is equal to how much the wave function will change in time. Again, taking a numerical approximation approach, we can add d psi dt to our current value of psi to get the value of psi at our next time step. So our wave function now equals 1 minus 0.2i. On the complex plane, taking the second spatial derivative was equivalent to multiplying psi by minus 2, which flips it across the origin on the complex plane. We then multiplied by 0.1, scaling our result. Now importantly, before we add this result to update our current value of psi, Schrödinger's equation tells us to multiply by I, which on the complex plane rotates our vector by 90 degrees to the left. We then add this vector to our current value of psi to compute the next value of psi. Repeating this process, we estimate the second spatial derivative of our new wave function, which again flips psi across the origin. We again scale and rotate by 90 degrees, and update psi with our new value of d psi dt. After a few more steps, a clear trend emerges. Our spatial derivatives are pushing our wave function around the complex plane on a curved or circular path. In the classical wave function, we can think of the spatial curvature as pushing the wave up and down in time, while in Schrödinger's equation, the spatial curvature of the wave is pushing the complex wave function in circles around the complex plane. We can get a broader sense for this behavior over space and time by considering a simple solution to Schrödinger's equation, known as a plane wave. This wave function is a complex exponential in terms of both position and time. Visually, this plane wave looks like a real cosine and imaginary sine, traveling to the right as time advances. Thinking of each point in our one-dimensional space as a little complex plane, the real cosine part of our wave moves left and right, and the imaginary sine part of our wave moves up and down. Taken together, these components form a complex number that moves around the unit circle as time advances, just as we saw numerically. Differentiating our plane wave twice with respect to position gets us minus k squared times our original plane wave psi. So just as we saw numerically, this spatial derivative is directly across the origin from our wave function value on the complex plane, and its magnitude depends on the spatial frequency k of our plane wave. Remember that Schrödinger's equation tells us to multiply this value by I to get d psi dt, which rotates our spatial derivative by 90 degrees. And it's this vector that effectively pushes our wave function around the complex plane. Larger values of k mean our plane wave oscillates more rapidly in space, increasing the curvature of the wave function and increasing the second derivative, which following Schrödinger's equation pushes our wave function around the complex plane faster in time. Plugging in the full plane wave into Schrödinger's equation, we can show that the plane wave is a solution and recover the exact relationship between spatial frequency k and frequency in time omega. This is the relationship that Schrödinger started with from de Broglie's matter waves. So our plane wave looks like spirals on a series of complex planes, and Schrödinger's equation connects the behavior of these spirals in space and time. Now, how are these complex valued matter waves at all a reasonable description of physical particles like electrons? Aside from including the imaginary number I, another important feature of Schrödinger's equation is that the wave function and its derivatives are not raised to any powers. This makes Schrödinger's equation linear, and means that if we have two wave functions, let's call them psi1 and psi2, If we add them together, psi1 plus psi2 is also a valid solution to Schrödinger's equation. This means that Schrödinger's equation will work for any combination of plane waves. For example, if we had an identical second spiral wave function, but shifted in space by half of a wavelength, the sum of these wave functions would exactly cancel out, resulting in an overall wave function that equals 0 everywhere. The ability of wave functions to interfere like this is critical to the wave-like properties of matter we see in situations like the double-slit experiment. Firing a stream of electrons through a single narrow slit into a detector, we see a smooth distribution of detections, where the most likely place for an electron to land is directly behind the slit, with this probability dropping off smoothly as we move further away from the slit. Now, if electrons were simply particles, when we opened a second slit, we would expect the distributions for the first and second slit to just add together, resulting in an overall detection pattern that looks very similar to the pattern for a single slit. However, in practice, this is not the behavior we see. As first demonstrated with electrons by Davison and Germer in 1927, we instead see a wavy pattern, where electrons almost never arrive at certain locations on the detector. We can make sense of this strange behavior of matter by using Schrödinger's matter waves. We'll represent the electron as a little packet of waves. This little packet is also a valid solution to Schrödinger's equation. And we'll switch from thinking in one spatial dimension to two. In 2 dimensions, it's more difficult to think of each point in space as a little complex plane. So let's switch to visualizing the amplitude of our complex wave function as the height of our surface. And we'll represent the angle of our complex number using the color of the surface. If we close one of our slits and pass our matter wave through, we see the matter wave spread out evenly after passing through the slit. Running our experiment again with the other slit, we see similar results. Now, before we run our experiment with both slits open, let's have a closer look at how our two patterns line up. Notice that the amplitudes of our wave functions are smooth curves, as we expect from particle-like behavior. But the angles of the complex numbers that make up our wave function change across the surface of our detector, and the colors from one experiment to the other do not always line up, meaning that our matter waves are out of phase at certain locations. This means that when we open up both slits, we expect destructive interference at these locations. Running our experiment with both slits open, this is exactly the behavior we see, with the electron's matter wave canceling itself out at these locations on the detector, matching the behavior we see experimentally. So the angles of our complex numbers in our wave function, also known as the phase, store important information about the matter wave of the electron, causing the wave to interfere with itself destructively at locations in space consistent with experimental results. A few days after Schrödinger submitted the final paper in his groundbreaking series, the physicist Max Born submitted this paper, including what today we call the Born rule, which, with some caveats, states that the square of the amplitude of the wave function is equal to the probability of finding the particle at a certain location in space. Following the Born rule, the amplitude of the wave function allows us to figure out where the particle is likely to be in space, while the angle of the complex wave function captures how matter waves interfere with themselves and other matter waves. There are other ways we can accomplish this behavior mathematically, but complex numbers are very convenient here, and it's interesting that imaginary numbers fall out of the classical wave equation when we combine it with de Broglie's simple matter-wave relationship as Schrödinger did. If we place our 2D wave packet in a box, the potential energy term in Schrödinger's equation will cause it to reflect off the borders and interfere with itself, resulting in a set of discrete fixed wave patterns. This behavior is analogous to the quantized energy levels Schrödinger found when applying his equation to the hydrogen atom in 3-dimensional space. It's remarkable that the same complex-valued wave function can describe the behavior of a free electron in the double-slit experiment, and the quantized energy levels we see for bound electrons in atoms. Years later, in a lecture in 1970, the great quantum physicist Paul Dirac had this to say about the wave function. So if one asks what is the main feature of quantum mechanics, I feel inclined now to say that it is the existence of probability amplitudes, which underlie all atomic processes. Now, a probability amplitude is related to experiment, but only partially. The square of its modulus is something we can observe. That is the probability which the experimental people get. But besides that, there is a phase, a number of modulus unity, which we can modify without affecting the square of the modulus. And this phase is all important, because it is the source of all interference phenomena, but its physical significance is obscure. So the real genius of Heisenberg and Schrödinger, you might say, was the discovery of the existence of probability amplitudes containing this phase quantity, which is very well hidden in nature. And it is because it was so well hidden that people hadn't thought of quantum mechanics much earlier. The phase Dirac is referring to here is the angle of the complex numbers that make up the wave function. Imaginary and complex numbers give us an elegant tool for representing and working with this phase, which is an integral part of how we understand matter to work on these small scales. The rise of quantum mechanics is such an astounding chapter in the story of imaginary numbers. The physicist Freeman Dyson writes that imaginary numbers showing up in wave mechanics is one of the most profound jokes of nature, and that the square root of -1 in Schrödinger's equation means that nature works with complex numbers and not real numbers. There's some debate to be had about just how essential complex numbers are here. Schrödinger himself seems to have never fully accepted a truly complex valued wave function, although he would go on to use it in his work and communications. What's absolutely awe-inspiring to me is that the numbers we rejected for so long as impossible or imaginary ended up showing up so profoundly in one of our deepest and most accurate theories of nature.